It's not what you thought when you first.
Okay, we're going to finish off section 5.3 on the normal distribution today, and specifically what the second part is about z-scores. Okay, so we're going to be talking about a standard normal distribution. We've already talked about normal distribution. Now we're talking about a standard normal distribution. So what's the difference? Well, the only difference really is in the numbers. So remember before we talked about a normal curve, it had that bell-shaped curve, something like this, right? And we said that if what went right here, what value went right here? That's the mean, right? So let's say we had a mean. Remember, mean is like that, mu. Let's say we had a mean of 30. Okay, so that would go right here. And then let's say we had a standard deviation. Remember, sigma is standard deviation of 5. And if that was the case, we would know one standard deviation above, of course, would be 35. A second one would be up at 40. And a third one, which would be almost the entire curve. Remember, not many values are above 3 standard deviations. That would be at 45, right? Just adding 5, 5, and 5. Same going down this way. One standard deviation below would be 25, another one below would be 20, and the third one below would be 15, and there'd be very, very few values less than that. Okay, so what we learned last time was how to do things like figure out what percentage of values are between 20, which is exactly this value, and 35, which is exactly this value. And then you could look up all the associated percentages in these regions here and add them all together. But the question I asked at the part of that video is, well, what if I wasn't asking you between 20 and 35? What if I was asking you between 20 and 32? Then you'd go from here up to here, but what percentage is shaded in there? And this is where the standard normal distribution is going to help you. It's basically exactly the same thing. So again, I'm going to draw that same kind of curve, a normal distribution curve, because it says normal distribution, right? And you still have the mean right at the middle, but now the mean is always going to be the same value. The mean is always going to be 0. And your standard deviation, so your mean is always going to be 0, and your standard deviation is always going to be 1. So your curve will just look like this: 1, 2, 3, and -1, -2, -3. So it's almost like just a renumbering system, the standard normal distribution. But the good thing about it is there's tables in your book, and there's functions on the TI-83 calculator that allow you to figure out any answer, even if they're not perfect numbers like we had here from 20 to 35. If it was 20 to 32, that's no more difficult using a standard normal distribution. Okay, that was a lot of information I threw at you at one time, so let's see if we can summarize. A standard normal distribution is a normal distribution with a mean of 0 and a standard deviation of 1, and that's what I showed you right here. And the other thing, which I didn't tell you, is the entire area under this standard deviation normal distribution curve is 1. If you were to add up all the area under this curve, it equals 1. Okay, next we have to talk about z-scores. A z-score indicates the number of standard deviations a data point is above or below the mean. So if, for example, we looked at some point right here, and let's say the value was 1.2, then any point along there is 1.2 standard deviations above the mean. I mean, we could also do that here, but it's not quite so simple to look at, right? If we were looking at this point right here, how many standard deviations is this above the mean? Well, that's no problem because it's 2 standard deviations above the mean. But if it was something like at 38, now we have troubles because we don't know exactly how many standard deviations above it is. That's why you'd have to turn that value into a z-score in order to figure out exactly how many standard deviations it is above the mean. Okay, there's a formula to convert a data point like on this first graph into a data point here. In other words, to find the z-score. And the formula for z-score is this. So obviously the z is going to stand for your z-score. The way you get a z-score is you take the x, which is a particular value, you subtract mu, which remember is the mean, and you divide by sigma, which is the standard deviation. And then once you do that, you'll have the Z-score, which you're able to look up on a table, which I'll show you in a second. Okay, Haley belongs to a running club in Vancouver. Below are normally distributed times for the 200-meter sprint in Vancouver and on a recent trip to Lake Louise. So the team went to raced in Vancouver, and the mean time for the whole club was 25.75, and the standard deviation was 0.62, and Haley's time was 24.95. Then they went to Lake Louise, and the mean time for the club was a little faster, the standard deviation was a little smaller, and Haley's time was also a little faster. And what we want to know is, where did Haley run better compared to the club results? Obviously she ran better the second one. Look at her time's faster. But we want to know relative to these times, which one is a better time. So the way we're going to do this is we're going to switch these scores into Z-scores, which we can then compare to each other. So this isn't too bad. For Vancouver, we're going to find a Z-score. And remember, the Z-score is equal to x minus mu divided by sigma. So in Vancouver, what's the time that we're interested in? What was Haley's time? 24.95. That's a 4. Subtract the mu, which is the mean. Well, the mean time was 25.75. And then divide it by the deviation, which is 0.62. You throw that in your calculator, and you get negative 1.29. Now, what does the negative mean? That means in your standard normal distribution curve, if the mean is right here, and the mean is what? How much? 0, always 0. Then negative is in this direction. Here would be negative 1. Here would be negative 2. So Haley's score for the Vancouver race is somewhere at negative 1.29. It's somewhere right there is Haley's score. So is this faster than most people or slower? It's faster, right? It's less than the mean. So pretty good score. Okay, now let's figure out how she did in Lake Louise. LL. Z-score is exactly the same. Same method to find it, So her time this time was 24.77. The mean this time was 25.57. And the standard deviation was 0.60. Divide those, you get negative 1.333. So did she do better or did she do worse? She did better, because negative 1.33 is further this way. There are fewer people that did faster than her. In the purple one here, all the people to the left here did a faster time. In the green one, there's a smaller number of people who did a faster time. So this is the better time for Haley. Better time compared to the rest of the group, right? It also happens to be her better time overall. Okay, next question. IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. If a person scores 119 on an IQ test, how does this score compare with the scores of the general population? Okay, well, let's draw a little bit here what we're talking about. What we're saying is, if we have a normal distribution, and the mean in this case is how much? 100, and a standard deviation of 15. So we could draw some of our standard deviations. The first one would be at 115, then it'd be 130, and then it'd be at 145. And if we go down, right, I just added 15. If I go down, I subtract 15, 85, 70, and 55. You probably can't even read the numbers. I've squished them all together here. And what we're wondering is, if a person scores 119, so they're right around here, how does this score compare with the scores of the general population? What we want to know is how many people, for example, have a smaller score than that. Well, this 119 didn't it didn't hit one of these perfect standard deviation spots. So we can't do this just by looking at this. We need to do something different, and there's actually two ways we can do this. One way is we can turn it into a Z-score. So let's do that first. Z-score is equal to x minus mu divided by sigma. What's the score we're interested in? What are we talking about here? We're talking about 119. What's the mean? The mean is 100. And what's the standard deviation? 15. And if you divide that, subtract, divide, you get 1.27. It's positive. Yeah, that makes sense because it's above the mean. The mean's at 0 and this is above. So what we've done is we've kind of turned this drawing here, we've turned it into, I'm going to draw it over here, we've turned it into this. Here's our mean at 0, our standard deviations at 1, 2, and 3, and -1, -2, -3, and now we're asking if someone had an IQ of 119, which is the same as 1.27 standard deviations, so that's somewhere right around here. I mean, it looks pretty much the same, doesn't it? The only thing's different is the numbers. So why did we bother with that? Well, we bothered with that because there is a table in your book. It's on page 188. It also goes to page 189, actually. And that has all the Z-scores on there. And it will tell you how many people got a lower score than that. So first of all, I'll make note of that. The table indicates the area or probability to the left of the Z-score. So our Z-score is 1.27. I'm going to go to the table. Mine looks pretty much the same as yours. And what I want to find is 1.27, right? That was our Z-score. Well, first of all, you start by looking down this left column, and you can see they're all negative scores. So keep going, and when you get to the second page, you'll see some positive scores. And one of the scores is 1.2, but we want 1.27. So where do we find the 7? The 7 is up here, right? So we have the 1.2 here, and the 7 there, and where they meet is right here at 0.8980. And that is the area that we're interested in. So let's go back here, and let's write that number down. 0.8980. That's the area under the curve, or you could also think of it as a probability. If you want to change that to a percentage, just multiply by 100, 89.80, which you don't need to write, percent. So 89.80% of people have a, what kind of IQ score compared to hers? They have a lower score. Because remember, the table shows you how many are to the left of that. So 89.8% of people have a score to the left of hers or have a lower score. Now, there's another way to solve this that doesn't require you to get Z-scores at all. And you can use your TI-83 calculator for that. And what you're going to use, and I'll show you after, you're going to use a function called the normal CDF. I'll show you where to find that. And I'm going to show you right now the numbers you're going to put in, and then I'll explain after. So you're going to put in a number like that, then you're going to put in this number, and this number. So let's go through what are these numbers. Well, let's take a look at the 100 first. What's the 100? The 100 is the mean, so that's easy. That's mu. What's the 15? The 15 is the standard deviation, so that's no problem. You're going to put in the sigma. And then for these two here, you have your bounds. This is the lower, and this is the upper bound, lower bound and upper bound. So a little bit of explanation there. If you're looking for a score of 119, which is right here, right? And you want to know all the people that did lower than that. So you're looking for all this down here. How many people did lower than that? Well, the highest value you're looking at is 119, so that's why it's the upper bound. The lower bound you might think is 0, but I don't know if I've actually mentioned this yet. These normal distribution curves go on and on and on and on and on and on forever, and it goes forever up here. It's just that there's so few data up here, so few people or whatever you're talking about up here, we don't really care about it very much. But really, it does go down forever, down to negative infinity. And the way you can put negative infinity into your calculator is you put negative some big number. Like, it doesn't have to be 9999. You could put 88423 or whatever. I just usually put a bunch of nines, and that's good. Okay, and this will tell you what percentage of people are below that value. So I'll show you on the calculator. Okay, so to find the normal CDF, you hit second vars, and you see it says distribution on top, and you want to hit number 2, which is normal CDF. CDF stands for cumulative distributive function. So you can hit 2 or arrow down to it. Now I'm going to put in those numbers. So I put negative. This is negative. this here is not negative, that's a takeaway sign. So negative 999, comma, 119, comma, 100, comma, 15. And if I hit enter, I get 0.897362. You can see our answer was 0.8980. Now we have 0.8973. It's even more accurate. So that's the other way you could do this, is to use your TI-83. Okay? Next question. Molly earned a score of 940 on a national achievement test. The mean test score was 850 with a standard deviation of 100. What proportion of students had a higher score than Molly? Okay, higher score this time, so we will have to take that into account. But really, we're just doing the same thing. Normal distribution curve. The mean right in the middle is 850. Whoops. So 850. Standard deviation is 100. So we go up to 950. 1050, etc., and down 750, blah blah blah, like that. The one we're interested in is 940, so right here, and we're actually interested in all the people up here. How many people have a higher what are we talking about, a test score than Molly? Well, the way we're going to have to do that, first of all, is to use the table. One way you could do it is to use the table, get a Z-score, and the table won't tell us higher, it'll actually tell us lower. So let's do that first, figure out how many people are lower. So we got to get our Z-score first. So the Z-score is equal to the value we're interested in, which is 940, take away the mean, which is 850, and divide by the standard deviation, which is 100. And if you do that, you will get 0.90. So remember, what we've done is we've taken this drawing and we've switched it into this drawing, the normal standardized one, as a mean of 0, 1, 2, and -1 and -2. And this value here, that 940, is 0.9 standard deviations above. So it is right around here. All we've really done is switch the numbers, and now we know how many standard deviations above it is. And we want to know what the area is below. So we're going to look up 0.90 on our table. Go to your table and go down to 0.9. So this will be on your second page again because it's positive. 0.90. So the next number is 0. So that's right there. 0.90. The number we get is 0.8159. So we'll write that down, 0.8159. Or if you want, you can change it as a percent, 81.59%. So what that means is, in the green area, I should have written this in green, because in the green area down here, there's 81.59% of the people. So how do we figure out how many people are up here? Well, total under there is 100%. So what you're going to have to do is 100, take away the 81.59, equals 18.41%. So maybe I'll write this. 81.59% of people have lower scores, and 18.41% have higher scores. Okay, and you're done. If you wanted to use the TI-83, you could use your normal CDF again. And remember, the first thing we're going to put is the lower bound. So what's the lowest thing we're interested in? The lowest thing we're interested in is her actual score, which was 940. How high are we interested in? We're interested in everything above that. So way up to infinity, or I'll put 9999. The mean is 850, and the standard deviation is 100. Should I show it to you that it works? Why not? It'll also give us a more accurate answer. So I'll clear this. I do second vars number 2, put 940, comma, 9999, comma, 850, comma, and 100. And the answer is 0.184, and that's exactly, if we turn that to a percent, it'd be 18.406. 18.41. Yes, that rounds to 18.41. So the TI-83 works as well. Last question. It's kind of the opposite sort of question this time. So what it says is running shoes lose their shock absorption after a mean distance of 640 kilometers. I'm going to write down this. The mean is 640. With a standard deviation of 160 kilometers. Zach is an elite runner and wants to replace his shoes at a distance when only 25%, don't know what that is yet, kind of confused, of people would replace their shoes. At which distance would he replace his shoes? Okay, so let's draw it out here. What we have is a normal distribution. The mean is 640. The standard deviation is 160. So going up, it would go at 800 and 960, etc., etc. And going down, 160 less than 640 is 480, and then 320, and then down to 160. And what we want to know is, when would only 25% of the people replace their shoes? Well, 50% of the people would replace their shoes on this whole half, right? Remember, this is symmetrical, and 50% on one side and 50% on the other. So if we want to know where 25% is approximately, this is very approximate, maybe it's, something like this. Somewhere around there. This area right here is 25%, or 0.25. And what we want to know is, what's the value right there? What's the x value right there? We don't know the x value. So if we look at our formula, z equals x minus the mean over the standard deviation. We have the mean, we have the standard deviation, we need one of these two things. What you can find is, using this 0.25, you can figure out the z-score. But this time you're going to do it the opposite way. This 0.25 is the area, or the probability, and you have to find what the z-score is. So you're going to use your table again, but you won't be going down here to look for 0.25. You're going to look in the main body here and find where's the value that's closest to 0.25, right? So if I look in the main body for 0.25, don't look around here, it says 0.02. I want 0.2. And I see 0.25 is very close to these ones right here. It's in between these two. So let's pick the one it's closest to, and that'd be this one. So that'd be negative 0.67, negative 0.67. So that is my z-score, is negative 0.67. So I can write that in. Negative 0.67 equals x minus u, which is 640, over the standard deviation, which is 160. And now we have to solve this equation. How are we going to solve this? We're going to multiply both sides by 160. If you multiply this side by 160, the 160 cancels, which is very good. If you multiply the other side by 160, you get 160 times 0.67, which equals, it's negative, so negative 107.2, and that equals x minus 640, and then we would have to add 640 to both sides, and if you do that, you end up with 532.8. So in other words, if he changes his shoes after 532.8 kilometers, only 25% of people would be replacing their shoes at that point. Okay, want to know how to do it with the TI-83? You're going to use a different function this time. This time, since you're doing the opposite or the inverse thing, you know the area under here and you want to know the x value, you're going to use inverse norm, and the numbers you're going to use are 0.25, 640, and 160. Where do these numbers come from? Well, the 640 is the mean, isn't it? The 160 is the standard deviation. Oh, I guess I'm supposed to be using these signs, aren't I? Doesn't matter. And the 0.25, that is the area under the curve, or the probability if you want. Okay, so let's show you that. We need inverse norm. So it's the same thing, second vars again. Inverse norm is number 3 this time. And we put in our numbers 0.25, comma, 640, comma, and 160. Hit equals, and we should get something very similar. I get 532.08, and our answer here was 532.8. It's pretty darn close. Okay, there's two ways to answer all these questions. One's with the table in your book. ones with the TI-83 calculator. I really don't mind which one you use, or if you want to figure them both out, that's great too. So good luck with that.
It's not going to stop.